can I foster that intelligence and change? That's been a key question in all of my training. It's not my question. It's half a dozen professors from Columbia in various forms have raised the same thing. Now, myself, my training has been as a psychologist, as a school psychologist. And the training has been essentially that of a scientist, with psychology being rooted in a science. So my definition of intelligence has been some scientific model for practice, as opposed to a philosophical or theological, or I guess if I wanted to really make some money, I'd be an astrologer. I'd make a hell of a lot of money on that. They're doing pretty well today. And their predictions are not too bad, apparently. But boards of education don't pay too well for astrologers. As a psychologist, I, to a large extent, was able to orient my practice along scientific lines. As a matter of fact, what we worked out here in the 5 towns was the 3R model, which has a scientific theoretical base that has governed our diagnosis and that has governed our practice. And when we began to see some holes or things that were not quite adequate in our model, we searched around for another scheme, and the planning group that put together this project reviewed a variety of theories and models, and Anisa was one that was accepted, and it, in our judgment, in my judgment, was presented, and what we're doing is looking at it as a scientific theory of education, with a couple of other adjectives in there. Not only a scientific theory, but a comprehensive, coherent theory of education. So I've taken some time to take a look at this to see, in fact, is it a scientific theory? My main thesis is that education as a whole is at a pre-paradigm stage. There is no scientific theory of education at this time. So when Dr. Jordan is saying he has a theory here that is scientific, and I'll begin to define science a little bit more precisely. I've done some soul searching on this and have taken a look at the theory. Let me just share what I've been doing, and let's run through it. For theory to be scientific at this point in time, definition of science, it means that it needs to be empirically based. Empirically based. But it's more than just simply being empirically based. If you have a scientific theory, you need 3 components in a scientific theory. The first one is observation. You begin with observation. You observe the real world. We assume that there's a real world out here. It's an assumption. From that real world, we make some observations. And that's the first step in building any scientific theory. And what you do in observing, in that first step, is you abstract some part of the real world. Let me just run through that very quickly. I summarize this this way. Any theorist, scientific theory, you need to raise the question is, what is their unit of study? What part of the real world did they abstract the study, to develop their theory from? Now, the physical sciences, their units of study are thing-thing interaction. Thing-thing interaction. Matter in interaction with other matter. And you have the major mature sciences of physics, chemistry, and so forth emerge from that. Psychology started, the units of study for psychology essentially were organism-thing interaction. Pavlov with his dog and bell sounds, the conditioning paradigm. Skinner and his Skinner box, which is organism-thing interaction. Now, social psychologists have their units of study that they built their theories on are essentially organism-organism interaction. That's really where we are in terms of, if you're going to have a science of teaching, you're dealing with organism-organism interaction. Sociologists, their units of study are organizations and institutions, how they function. Historians, Toynbee's units of study were civilizations. The 21 civilizations were his units of study. He didn't study city-states or nations, he studied civilizations. So if you're going to have a theory, any theorist developing a theory, you raise the question, what are the units of study? Now, what are the units of study in the Anisa-Model? Now, you look at how comprehensive that is. The units of study, the basic unit of study really is change, isn't it? Energy transformation. And these include not only the physical, the biological, the animal and human and the unknown. It runs the whole spectrum. So if you look at what the units of study are in the Anisa-Model, it is, I guess, subsumed under that first concept of change itself, which runs the gamut from the material to the spiritual level. Okay. So quite clearly, the Anisa-Model, in terms of what it observes, it's proverbially handling the entire elephant. You remember the story, the fable of the 5 blind men and the elephant? And it's really one of the most comprehensive theories that takes on really not only a cosmology in terms of history and the universe, but all of the other elements in between. Okay, now, the second step, if you have a theory, a scientific theory, you represent the real world over here in some symbolic form. And the next step is really model building. And there are 3 steps in model building. Now let me just simply say something about models. You know, the word is never the thing. The symbol is never the thing. It's a representation. It's a symbolic representation of what's happening. Now, there are a number of symbol systems that we can use to map the world. One is mathematics, which most of the mature sciences use, language, and the arts. Now, in model building, there are a variety of models. There are simulated models, where if you can't deal with the whole thing, you make a simulated model, a wind tunnel model of an airplane. That's one kind of model. And there are abstract logical models that are mathematical models, but they have no direct representation in reality or in nature. Now, the kind of model I'm talking about here, and most scientists refer to, is what we call theoretical models, where it's a symbolic system, but there is a concern that there is some relationship in terms of what operates in the theory and what goes on in nature. So we're dealing with a theoretical model. And it'll become a little bit clearer here because I have a suggested change that maybe it's not the Anisa-Model. It may be more appropriate Anisa paradigm. Let me get to that. Now, in model building, any scientist who builds a model needs to have 3 components. One is a data language. In physics, the data language, we're dealing with matter, space, time, energy. Those are part of their data language. If you take some of the behavioral sciences, learning theory, you have stimulus response, stimulus organism response, reinforcement, primary. These are all the data language. Freudian theory, id, ego, superego. This is the data language. Now, the important thing about data language is there a precise data language that has some relationship or some referent in the real world? If you're looking at a model, this is what you need to look at. Now, look at the Anisa-Model. We've been very, very careful here in the presentation of the data language, quite precise terms, and you're familiar with those. And in general terms, the Anisa-Model does fulfill that criteria, those criteria of having clear and precise terms or data language. Now, another thing that any theory has, if it's going to have a theory, are assumptions. And these assumptions are either implicit or explicit. For example, the assumption underlying the Newtonian model in physics is that the natural state of matter is at rest. That would remain at rest unless there's a force either directly or at a distance that would move it. That underlies the Newtonian model. The shift in assumption that Einstein made, it really put a very different perspective on this when he shifted the assumption. Einstein shifted the assumption that the natural state of matter is not at rest, but the natural state of matter is in motion. Matter is in motion. That's his relativity. You have to take into account the speed of the planet or platform that you're on vis-a-vis any other, and that the natural state of matter is in motion. Newton used a Euclidean geometry to map his notion of his terrestrial and celestial laws. Einstein had to shift to a whole different mathematical system, Riemann's mathematical system. But the shift in assumption made a major change in the theory. For example, one of the major assumptions we're concerned with in the behavioral sciences, and I'll come back to this a number of times this afternoon, is the assumption underlying the Skinnerian learning theory. The basic assumption there is that man is reactive. He is a reactive organism to efficient causes. If you look at the Anisa-Model, the Anisa-Model makes explicit what its underlying assumptions are, and those assumptions are closer to the organismic philosophy, that man is not simply reactive, but he is proactive. A very different assumption, and it changes the view considerably. Now, some theories have their assumptions explicit and get them out front. Others, they are simply implicit or are not very clear. Now, again, with Anisa, the very basic underlying assumption of the Anisa model is going back to that first principle, which is change and the translation of potentiality into actuality. It has a very different assumption about the nature of reality. Now, other assumptions, let me just give you another one which developed in the physical sciences. The second law of thermodynamics, which is concerned with the motion of molecules in the universe. If you have a closed universe, the molecules are slowing down, they'll be randomly distributed, and essentially chaos exists. There's no order. Now, information theory, communications theory, cybernetics, and general systems have operated on a shift in assumption. He said instead of the universe being a closed system, as the second law of thermodynamics indicates, and the word they use there is entropy, they have a shift in assumption that there is negative entropy. Negative entropy in a sense that there's an organized complexity. There are forces that operate that tend toward higher levels of organization and integration. Very different assumption. And that shift in assumption, that was really a breakthrough in terms of Norbert Wiener, in terms of the Second Industrial Revolution. That is the basis for our TV, communications, computers, and so forth. That technology has been really worked out very well. They are way ahead of us in terms of where we are in education. Okay. Now, the third, if you have a scientific theory, if it's a good scientific theory, it should be able to generate new and testable hypotheses. Now we have a lot of theories. But unless the theory is able to be tested in the real world, unless we're able to see with the theory, I guess I can put it down here, see the real world too in a different way, or be able to test your hypothesis in the real world to empirically verify that, it doesn't qualify as being a scientific theory. It may be a metaphysical theory, maybe a theological, maybe something else. But that's the essence of what we would accept today as a scientific theory, the ability to empirically test the hypotheses deduced from the theory. Now, we look at the Anisa-Model, and are there hypotheses that can be deduced from the theory and then tested in the real world? That's the essence of whether this is a scientific theory or not. Okay, I don't know whether you can see. Can you? We didn't get an overhead in here. The Anisa-Model is built on the theory of evaluation being at the fountain, or at rock bottom here. And then that theory of evaluation will be continuously evaluating and re-evaluating the philosophical basis of the nature of man, both sides. Then there's the theory of development, theory of administration, theory of curriculum, theory of pedagogy, which are continuously being evaluated. This forms the empirical base for being able to test out the theory of pedagogy, theory of curriculum, and always questioning on some empirical base those first assumptions, that is the philosophical basis of the nature of man. Now, I guess we could stop here and say, in essence, we have a scientific theory. We can document this more fully. However, as you go from hunchland, this is hunchland here, into the land of verification, that becomes a very big bridge to build. Through designing experiments, or what we're doing with Anisa, field testing it at various sites, gathering the hard empirical data to see whether in fact it works. Designing such experiments or testing it out becomes a monumental problem as far as methodology is concerned. Now, the growth of knowledge, growth of scientific knowledge, from Francis Bacon down to Karl Popper, who takes this position. The way they would be able to test one theory against another theory is to empirically test it out in the real world through experimentation, and if the evidence is such that the theory is validated or proved false, then decisions could be made as to which theory would be acceptable. That's the building block theory of the growth of knowledge, which Popper and many hold on to, and that fits very much the mechanistic paradigm. I would like to suggest to you, however, that that is not the way the growth of scientific knowledge develops. And Thomas Kuhn, in The Structure of Scientific Revolutions, takes another perspective in looking at how knowledge, or scientific knowledge, grows. And it does not take this development by accumulation or accretion. You know, each scientist offers something and there's a building block and you just add on to that. He suggests, and his main perspective is, that the growth of knowledge follows this process, and let me spell it out. That at a point in, well, there may be observations, experimentation, and some empirical testing This has gone on from the time of Aristotle forward. So some element of science has been taking place. The issue that we have here is when you raise such questions as when, for example, was oxygen discovered and invented. Okay? The historians of the theory of knowledge don't come out with a very precise direction. It doesn't fit this accretion process or the accumulation of knowledge. When Priestley discovered it, and then Lavoisier also worked on it, they were dealing with phlogiston theory. They were really not aware that oxygen was developed. So you can't give credit to a particular person or something in time. Then the other issue here is the knowledge that, or the scientific knowledge that existed in the 16th century, which when it's compared to present scientific knowledge, which is obviously false, was it less science, or was that superstition or clear-cut error? You can't answer the question. Because we're using the same procedures today in terms of observation, experimentation, and so forth to arrive at knowledge. And therefore we could be also subject to the same error or superstition and not be science. So this notion of the development or the growth of knowledge does not really follow this, and that's my thesis, and that's what I'm saying here, but it follows a different pattern. Now he uses the word paradigm, P-A-R-A-D-I-G-M, and I'd like to use that. Prior to the development of any paradigm in science, there are theoretical schools who deal with some component of reality. They have a research program, they have some theory, but typically what you have is a variety of schools, any one of which is competing with the other. They probably spend as much time referring to or reacting to other theoretical schools as time dealing with reality or dealing with nature. To that extent, education to a large degree is at a pre-paradigm stage. We have a lot of theoretical models, each competing. I teach at several schools, and I have to say, here's the learning theory model, here's the psychodynamic model, here's Glasser's model, you take your choice. This is really what it amounts to. So to this extent, education is largely at a pre-paradigm stage. Now, now a paradigm, to develop as a paradigm, a scientist or the creator, the forerunner of a paradigm, there's a development of some exemplar, some outstanding scientific work. Let me take Newton's, for example. His basic exemplar was force is equal to mass times acceleration. The underlying assumption there was that the nature was made up of matter, and he was concerned with matter in motion. And you take the variations on this force is equal to mass times acceleration is really the key that has gotten us out to the moon and elsewhere. His terrestrial and celestial laws are really built on variations of this, his three basic laws, but this being the key. Once scientists accepted this as here's how nature works, then you get into a complete research program. Scientists then are trained within that paradigm. This determines what are legitimate research problems that are legitimate for study. The research and the theories then are articulated, a great deal of instrumentation and precision develops, and the paradigm develops or goes into what we call normal science. Now, when you're in the normal science phase, that is the time when a great deal of the fleshing out, the testing out against reality of the model, does it fit? Now, let me run through very quickly. Now, the growth of knowledge, then, is there a paradigm develops, there are people who are then trained both in theory as well as in practice. The implicit kind of learning that you get, that engineers get working with this. It's not just concept, you have to really work with it, the intuitive kind of learning that you get. Another exemplar, for example, of the behavior science would be the Skinner box. If you've ever worked with pigeons or learning theory in the Skinnerian model, there's a lot of implicit learning that takes place. And if you had that and then you take it out and apply it as the Skinnerians have, and many of us are involved in that, and you see the whole research program that has developed from Skinner. Tremendous number of doctoral dissertations and research programs supporting that theory. Now, in the growth of knowledge, what happens is that anomalies now begin to appear. That the paradigm which determines legitimate problems for study, either through instrumentation or they expect to find something in an experiment and it doesn't come out that way. And so therefore an anomaly appears. Now the people who are within that paradigm usually do not look for novelty, and they sort of ignore that anomaly. They get an ad hoc assumption, or they deal with it. Well, it wasn't the theory, maybe their instrumentation. They blame themselves rather than tool, rather than blaming the theory. But these anomalies persist, and others show up. Then the science enters in what Kuhn refers to as a crisis. There's a crisis. Now the crisis then is resolved in his concept of the growth of knowledge by the development of a new paradigm. And this frequently takes the shape of what might be referred to as a paradigm shift. Now let me give you some classic examples that you're all familiar with in terms of this process. The most notable one is the Copernican revolution. You know, the concept before Copernicus, that Ptolemy built, was that the Earth was the center of the universe and the stars and the sun revolved around the Earth, the geocentric concept. And if you take a look even now at a lot of the empirical data, that little ball, from an empirical point of view, in terms of what you can observe, that makes a lot of sense. It was a significant scientific revolution when Copernicus came in with his paradigm, which indicated a heliocentric notion, that the Earth is a planet that moves around the sun. By the way, that was not very readily accepted at the time. He threw him in jail. Look what they did to Galileo when the instrumentation was developed, the telescope, suggesting that there were imperfections on the moon. They almost burned him at the stake. You see, the paradigm dominates. It's a worldview. It tells you how the world works. And people who are then committed to that paradigm, for them to give it up, it's like committing suicide. It's like committing professional suicide. It's a very difficult thing. Most people do not abandon their paradigms. They simply die away, typically what happens, or they will change if there is a constructive alternative. You cannot convince somebody that through this kind of a process, rational, logical process, which what Popper and those people who hold this view, that you look at the data and it's a rational process, you shift. Well, if you look at the history of the growth of scientific theories or scientific knowledge, it does not follow this pattern. I think this pattern is an inadequate way of dealing with reality. It is very much within the mechanistic paradigm, which I'll now come to. The people will shift to a new paradigm if the new paradigm is an alternative that can deal with the anomalies, and handle those by conceptually, as well as dealing with the data that existed in the old paradigm. Now, another paradigm shift, clear paradigm shift, was a shift from the Newtonian paradigm to the Einsteinian paradigm. We did not have to give up Newton's first three laws, the inverse square law of this and the other, in terms of his terrestrial and celestial laws. But they were made special cases when Einstein introduced his theory of relativity. It not only explained Newton's laws, but it gave us a different view handling some of the anomalies that existed. Let me just make an observation here in terms of a theory of a very general nature, such as Einstein's theory of relativity. There are only four, and about a month ago, some scientists at the University of Massachusetts came up with some other evidence which I have not seen, and I'd like to see it. But there are only four empirically verified, that is, where there's evidence in the real world that Einstein's theory in fact holds. The first one is dealing with a red shift, that the universe is expanding. Since it's expanding, we have the red shift. That's related to his. The second one is that light, which is a photon, which travels at 186,000 miles per second, when it passes through a heavy gravitational field, will be deflected by that gravitational field. And the experiments, the total eclipse in 1919 was the first evidence when they looked at the total eclipse of the sun and the star just beyond the penumbra of the sun, that light from that star would be deflected as it went through the gravitational field. And more recently, those results are equivocal. There's question on that. And there's another one in terms of the precession of the perihelion of Mercury, which the Newtonian theory could not handle, and Einstein's handles very well. And there's another one by Bussard and the third one. There's not that much empirical evidence, and yet there can be great support for a theory. I think that's important for us to understand in terms of the Anisa theory, which is a very broad and general, that we're not going to be able to get very definitive, at this point in time, empirical evidence that fully supports the theory. Okay. Now, what a paradigm does, a paradigm is a worldview, if you will. I think, Linda, you presented that picture on perception where you could it looks like a duck or a rabbit. Let me use that. Weinstein, Wittgenstein uses this, that's his. That when you have a paradigm shift, if you're looking at the world through a particular paradigm, if you were to look at that design, maybe all you could see is the duck. You can't see anything else. When you have a paradigm shift, if you're able to look at the world now through the new paradigm, very frequently you could then see it both as a duck and as a rabbit. Okay? You can flip. But people who are trained in a certain way to see the world, and the paradigm determines that for you, you tend to see the world that way and you cannot see it in the other way. People who are looking at the world in one paradigm and people who are looking at another paradigm, they cannot communicate. This is what Kuhn indicates. It is incommensurable. They're using different terms, and they don't mean the same thing. Let me give you an example. The term atom, as used by Democritus or Dalton, is very different. It's the same word as the current use that atomic physicists are using. When you use matter in terms of Newton, which was matter takes up space and has weight, it's very different from the meaning that Einstein gives to matter in his, which is expressed in his famous equation, equals mc squared, where matter and energy are equivalent. He hyphenates it. We're using similar terms, but they view the world in a very different way. Now, boy, time is fleeting. The dominant paradigm that we are under, scientifically, is the Newtonian, the Lockean, John Locke, that British empiricist, and Newton, which is the mechanistic model of the universe. And the metaphor that we use there is basically that the universe is a machine, whether it be a computer or a clock or it's some kind of a machine. What we are concerned with in that mechanistic model is we are concerned with efficient causes. So that there is some force or some efficient cause operating on matter or operating on you and me from the outside that causes us to react in some way. Efficient causes are always linear. There's a cause and effect relationship. And the cause and effect relationship is linear. And if the mechanistic model is correct, if you determine one of the universal laws in terms of cause and effect, that law is applicable throughout all time, past and present and future. And if we were able to, as scientists, in this mechanistic way, to understand how nature worked, we would be able to understand what all of these cause and effect relationships are. We would then be able to predict and control for all time. We would understand. Now, all of my training as a psychologist has been essentially under that paradigm. And that's what we talk about when we're being scientific. We want to be objective. Skinner's model is very effective that way. Skinner deals with the empty organism. All he's concerned with are learning curves. And you set your contingencies and your reinforcement schedules and you get a certain learning curve, built on the assumption that man is basically reactive and reacts to environmental efficient causes. And we can isolate this. That's the model. That would be what are called the hard methodologies. These are hard data. We set up designs then that have, and we were meeting this morning, setting up designs here as we're evaluating this project in terms of what's going to happen to the youngsters. We're going to get some control groups. We're talking whether we get randomized groups, get control groups. You know what you're doing. You're isolating the different groups so that you can determine what the cause and effect relationships are by being objective. Ideally, what we could do here is set up some double-blind kind of, I don't know how you do it with what we're doing, but that's what they do in pharmaceutical work particularly. But the idea there is to be objective, Now, any number of anomalies now are cropping in with the mechanistic paradigm. Let me stay with learning theory, with Skinner's model. One of the problems, or basic to the mechanistic model, is it tells you how reality is, what reality is. It deals with the what is question. It does not deal with the axiological or value questions, ethical questions. Skinner is very clear that his techniques are neutral. They can be used by a saint or a sinner. We learned that in the Korean War, that they used the learning theory techniques in brainwashing our soldiers. But the techniques were deduced right from learning theory. That's an anomaly that the theory proposes for us, that it cannot answer, it answers the what is question, but it does not answer what ought to be. Now, Another anomaly that is posed by the mechanistic model is this problem of object and subject. Object and subject. You see, to implement the Skinnerian model, and if we were implementing that with our youngsters, we would be strictly objective about that. We would control our environment, control the contingencies and reinforcements. We would be treating our kids as objects. And that's an anomaly. If you want to build your program based upon that theory, you have some major problems. And some of these are at face value. Why our parents react to behavior modification. Why I react to behavior modification. Why we try to modify our 3R program to go from the locus of control being external to internal. Because we were grappling and attempting to deal with the moral and ethical issues that are involved, that are implicit in our Judeo-Christian Western world, which operates on quite a different view of man. Now here's where, there are other examples that I can give, I'm running out of time. Let me just build on those too. What Dan has done, Dr. Jordan has done, in the Anisa-Model, and here's where I'm indicating that the Anisa-Model now is, and perhaps the term is inappropriate, where I'm suggesting that it is a paradigm. It is a new paradigm. And I think he represents a major paradigm shift, as analogous to the Copernican from the geocentric to the heliocentric, or from Newton to Einstein, where he introduces now this notion of subjective aim and final cause. Final cause, as you know, deals with purpose, with goals. And that now operates on a very different assumption. And the assumption, and here's where there's the real paradigm shift, is that Dan shifts from the mechanistic to an organismic view. An organismic view. That we're dealing with wholes. In the mechanistic view, you try to break the problem down in terms of, as I talked about before, by a reductionist notion, by trying to explain the whole by breaking down into its subparts, breaking it down into independent, dependent variables, and breaking it out that way, as if you could understand the whole by breaking it down into its parts. Well, there seems to be question as to whether reality works that way. The underlying assumption of the organismic approach, or what Dan is talking about, is that man is not reactive, just reacting to efficient causes, but is proactive. Going back to Leibniz and to Whitehead and the others, is that it is the essential nature of all things, matter as well as, and particularly at the human level, this ontological development, that we are not simply reacting to efficient cause, but we have subjective aim and there is purpose and we react that way. You see, it tends to resolve some of the anomalies that exist in the mechanistic paradigm. Now, let me just simply, Dan has, you go back in your notes, this does not rule out efficient cause. We are still reacting to efficient cause. If I jump off, if I stand here and go down, I'm still going to be reacting to efficient cause of gravitation. Efficient cause is still operating biologically in terms of your genetic and neurological and other components. That still exists. But that is not the map of reality. That is not the way reality works. This is what the new paradigm is suggesting. And Dan has spelled this out in terms of evolution, that there have been leaps in evolution where man has been freed from instinct. You see, lower forms of life are still highly governed by instinct, by efficient cause. But there have been leaps in evolution, where, and particularly man is at one of these leaps, where he has been freed from efficient cause, and learning has been brought to bear, So he has some freedom of choice, certainly more freedom of choice than exists at lower ontological levels. And if you didn't have that freedom of choice, how could you have ethics or how could you have responsibility? If you're simply reacting to efficient cause, you're not responsible for your behavior. That's simply inherited. Can you see some of, I'm fumbling around here a little bit. I'm jamming a lot in a short period of time, and I told you I was going to be up on cloud 9, but I hope you're tracking with me and seeing where I'm coming from at least. That's the reason I can say that Dan's model represents a paradigm shift, because we do not have to give up the mechanistic components. But the mechanistic components, or that model, or that paradigm, in terms of how reality works, is limited. And there is more than just the mechanistic notion. And here's where he has the paradigm shift of introducing subjective aim, final cause, in terms of this organismic view of the world. We get away from the simple cause and effect relationships, or breaking problems down into independent, dependent variables. We are concerned equally with reciprocal causation, rather than linear causation. There are a whole host of significant differences between the two. Now, let me use another example in terms of evaluation. When a paradigm moves into normal science phase, the paradigm rather determines the kinds of problems that you're going to be dealing with, or what are legitimate problems. And a great deal of research and empirical work takes place. For example, under the mechanistic paradigm, which I was trained under, and most of you were trained under, one of the problems we had in evaluation were concerned with developing instruments that could evaluate, for example, intelligence or achievement. Now, let me flesh this out rather quickly. The underlying assumption that existed, or that exists there, is that the trait is randomly distributed in the population. So intelligence is randomly distributed in a population. Achievement for reading, math, and so forth is randomly distributed. The mathematical model that that mechanistic approach used to try to map that was Fisher's unit normal curve. Things are randomly distributed. You have a random distribution. Now, what Binet did early in the turn of the century, he operationally defined what intelligence was. He took a number of items, vocabulary and so forth, gave them to a random sample of kids, and saw how they responded to this, imposed a unit normal curve, and then defined intelligence as relative. We had so many kids who were 50% fell below the mean, 50% above, and he defined intelligence objectively now. See, heretofore you defined intelligence in terms of whether they're smarter than you or not. And the same thing is a thermometer in terms of heat. See, the thermometer was an objective instrument that determined on a scale, Fahrenheit or Celsius. I'm more familiar with Fahrenheit. I think I'll never convert from that paradigm. Or it's not a paradigm, the other. I just can't convert. But that was an objective way, because otherwise you just simply had to indicate whether it was warmer or you were warm. You might have had a fever. There was no objective way. Well, here was a nice objective way of developing this. Now, the assumption was a random distribution. The mathematical model they used was the unit normal curve. Then the technology that developed were normative tests, which you and I know as standardized tests. Very objective. A great deal of research has gone on in that field over the last 75 years. Under that paradigm, really being objective, objectifying it. No. One of the problems with this is, and here's where we practitioners have attempted to use these measures, and educators have taken this on, and we're being very objective when we do this. And here's where I think there's some real misuse. What it does tell you when you evaluate a youngster, it tells you where this youngster stands in relationship to some reference group, either third graders or sixth graders or whatever your norm group is. It tells you where he sits someplace on that continuum. But it does not measure growth over time. It does not measure how that youngster, we do not have a scientific model to tell you how that organized complexity of how those atoms that have been flung together to make Grace McFarland or me, how we have changed and developed over time. This is not an accurate map of that. It simply tells you where you are on a continuum. It's an inappropriate measure of change over time of the individual or the group. Now, the Nisa paradigm now poses a new problem for us. How then do we evaluate or measure change of the individual over time? That poses some new problems. And in paradigms, I make a distinction, or as Kuhn makes the distinction between problems and puzzles. In a paradigm, we are concerned with puzzles rather than problems. You know, solving the housing problem, there's no solution to the housing problem. But if you start here, it's going to go here. But in science, when you're working under a paradigm, there is a solution to the problem. It's a puzzle. It's just like playing bridge, or there are certain rules if you follow. There are certain rules if you follow here, you'll get you out to the moon in a very predictable way. It's a puzzle that can be solved. Well, under the mechanistic model, in terms of evaluation, they had a puzzle. It was solved this way in terms of normative tests. This paradigm is posing a new puzzle. I don't know the solution. I know the problem. And I think here's people who are going to be working in this paradigm over the years. That's a nice problem to get a hold of to solve. We may need a new mathematical system, maybe ipsative or non-parametric statistics, but that still has a normative notion. But the technology is such, developing as such in terms of computers, that we may be able to gather information, be able to map this over time, and develop a new kind of technology that can get to what we are calling process here. Now, some things are already, oh boy, look at that. Well, look, you can,
2 minutes.
2 minutes. Okay. Guess what I'm proposing here is, that in my writings now, because I'm convinced, and I'll have to clear it with Dan, that I'm not going to refer to the Anisa-Model, I'm going to be referring to it as a Nisa paradigm, because I think it's very broad in scope. I think it does what Newton did in terms of describing reality. I think those first assumptions, those first basic principles, really tell us how reality works. Now, what we are attempting here, and if this is a new paradigm, there's a lot of work here for a lot of us to do. We're at the very beginning stages of a new paradigm. I guess the sensitivity, or at least increase your awareness of some of the problems here when we're going to try to communicate with other people who are oriented in the mechanistic paradigm. You're not being objective. I think we need to then really redefine what we mean by science. That this is scientific, it represents a scientific paradigm shift. It can handle most of what we have under the mechanistic. I have no real difficulty with that. But we have a new worldview. We have a new set of problems for evaluation. How do you evaluate the whole? Let me give you this one example, which Dan has already alluded to. And strangely enough, we have some examples from the physical sciences. If you're concerned with not the reduction notion, breaking the problem down into its subcomponents, but you're concerned with wholes, the holistic approach, the organismic approach, we're then concerned with the whole being equal to more than the sum of the parts. Equal to more than the sum of the parts. And let me use Buckminster Fuller's example, synergistic example. If you take a nickel, iron, nickel, aluminum alloy, if you take the tensile strength of iron, which is about 50,000 pounds per square inch. If you take the tin, I think it's about 60,000 pounds per square inch. Don't hold me to this, I'm doing this from memory. And you take the nickel, which I think is about 70,000 pounds per square inch. You add up the total tensile strength of that, and it comes about 250,000 pounds per square inch. Now, if the mechanistic model were correct, in terms of the reductionist notion that we would understand the whole from the subparts, we would have an alloy that had 250 pounds per square inch tensile strength. In fact, what you have is 360,000 pounds per square inch, and that's the alloy that they use in jet engines that can handle the pressures of jet engines. Those components come together in a new whole. It's that more. Now, this is equally true of you and me. We are more as we develop, from even in Piaget's terms, from one stage to the other. When we move to a higher stage, that higher stage is a new level of organization that cannot be understood from breaking it down into component parts. Now, that's a whole different paradigm. That's a whole different way of looking at the world. And we're going to have difficulty in terms of the hard methodology. Now, what this does is legitimize what we call some of the soft methodologies in the behavioral sciences, and particularly in management. Because what it legitimizes now is participant observation. You don't want to be objective because you are a participant observer in this. It becomes very important. Just as you're participating in this field testing of the Anisa-Model, we're very interested in your perceptions. We're using the circular and feedback process because we are going to be at different stages, and we're going to evaluate the outcomes at different stages. I certainly can't evaluate what our first year, where we're just giving theory just a level of awareness, with what may your own reorganizations after 3 years, what that would look like. And that whole process of change, of planned change, because it's not only operating with the youngster, but with you and me, and we are a part of it. And the thing that intrigues me about participating in this model is many times I see the universal, universal in particular in terms of what I'm doing. I appreciate it. It gives me some structure. And it really has answered my first question, what does it mean to be intelligent with respect to personal social change? Here is a scientific model that's more than a scientific model in the sense that it's a new paradigm. It's my answer to what is intelligent, and it's my answer, and it really is a most elegant answer to change. Heretofore, I was looking at change in terms of being a revolutionary or a social reformer or planned change. This is really just the most elegant thing because that is the first principle of change, and to see how universal that is. So I'm just excited, as you could probably see, in terms of my professional career, to be able to be involved with this, but not, and I don't know how Whitehead characterizes this, but if you don't use knowledge and put it into practice, it's inert. And I'm just delighted to be working with a hell of a lot of you who are working in this paradigm, and we're going to be trying something out. Okay, thank you.
Fill out another interaction, and we will bid you adieu. Did you just write the theory of evaluation at the top? So we'll differentiate. Theory of evaluation. I'll just kind of straighten that.